Welcome to EduAmp. This is an A-level physics lesson all about refraction. So what I want you to be able to do at the end of this video is describe and explain the principles of refraction, state Snell's law, and then start performing calculations using Snell's law. Now, this is all to do with light and refraction. One of the important things you might have seen in GCSE, you need to get your head around, is model with waves, etc. So I want to look at this really cool simulation down here. I'm trying to get hold of it. Okay, so imagine you've got a pool of water. Now what you can do is you can put a droplet into a pool of water and it starts giving you these waves going out. They're circular waves. Now these are called wavefronts that are going out, but you can probably see dark and grey areas. And to show you what the dark and grey areas are, what I can do is very coolly go on to a side view. So as the droplet goes down here, the waves are travelling out like this. Now you've got peaks and troughs. If I pause it here, obviously it's going to be a trough and there's going to be a peak. So when I go back to the top view and I've got the waves going out again, what you're seeing is, no matter which way you look at it, the bright and dark is the peaks and the trough as the waves head out. Now we call the distance from the peak to peak is going to be the wavelength, which is going to be over here, and the height of the wave we call the amplitude. And I can change here the amplitude to be low, and you can see the waves hardly go up at all, and they can make the amplitude bigger. What's a really cool thing to do as well is you can actually make the water droplets go up more quickly, and if they go up more quickly, you probably see the waves are more cramped together. In other words, the frequency changes the wave. And I go in the top view here, you can actually see here the waves are close together and they make the frequency less. Now the waves get more spread out. And that's because during the wave equation, frequency and wavelength are linked together with speed. Now, to get back to where we're going with this is, therefore, if you've got light here, what we do is we represent the light could be basically coming from a bulb. We could just have here right in the center, and the light is then spreading out. Now therefore light is modeled like water waves. So what you can see here is going to be your peaks and trough heading all the way out here, and we draw the direction of the wave, and it's always going to be perpendicular to the wavefronts. Hence light, but the light bulbs here, light is spreading out like a sphere. We can do a 3D mode, coming out in all different directions here, and you've got your circular wavefronts. Therefore the light is basically coming out in all directions you can see. So what we mean by a light ray is like modeling the water wave, and the light ray basically shows the direction of the light as it goes away from its source. Therefore, when light then passes through a transparent, and I'm going to mainly look at this as a glass block, is you get something called refraction. Now this is a practical you should have done at GCSE. When you had a light ray coming in here and it travels from air into a glass block. Now we call this line all the way along here, this is called a normal line. We then call the angle between the instant ray, and here's your instant ray just here, and the normal is called the angle of instance. Then when it goes from air into glass, it then bends towards the normal, and here's going to be your refracted ray just here. Hence the angle between the normal and the refracted ray is called the angle of refraction. When then again it merges just here, now going from glass back to air again, now you've got your normal again just here, and again you've got your angle of the instance here, and here's going to be your angle of refraction. And you can see the angle of refraction is bigger now than the angle of instance. Now you need to know why this happens, why refraction changes the direction of the wave as it goes through, or the light wave it goes through. So this is a really nice simulation here. What you've got is your normal line just along here. Here's going to be your angle of instance. There's going to be your angle of refraction. This is going from air into glass. Now, as I mentioned before, we can model waves by looking model them on water waves. So here's going to be your peaks and troughs of the water waves coming along here. Here they're traveling through air, and now they're going into glass. Now, if you look very carefully, you can see the waves traveling along here they slow down as they go from air into glass. But because it's going at an angle, can you see just here they slow down first? And I can't freeze it. Here they slow down first, therefore the waves slow down just at this point here. Here the waves only slow down just at that point. And because these waves slow down here first, what it does, it changes the direction of the wavefront. Now, if I get into combine mode, like I showed you here, perpendicular shows the direction of the light ray, and you can see now because the waves turn, hence the light wave changes direction. So really start thinking about it, it's all to do with slowing of light. Because we say this is an optically more dense medium, it slows down the light going from air into glass. The light finds it hard to get through. Now, with that, doesn't this make sense? If I now take my wave and I'm going to now change the angle of instance and I'm going to get bob on the normal. If you put it along the normal, you can see now the light wave is not changing direction at all. Well, why? Because isn't now the wavefront slow down all at the same time, therefore it won't change direction. And that goes in our model explaining refraction. So what I've now done is shown you why refraction happens. Hence, a lot of physicists started doing work on this, and they started to look at the fact, well, is there a link between the angle of instance and angle of refraction? Well, Snell did the work and eventually came up with Snell's Law. Now, what you do in a physics lab is you get a semicircular glass block. You then get a light beam here, and my model diagram here got a laser. And what you do then is you now have this shining from air into the glass, which is just going to be here. Okay. Now, here's going to be your normal line, and I'm just going to sketch it on, try and destroy the picture for you. And what you can do is measure the angle of instance and the angle of refraction. Now, we use a semicircular glass block because when it comes out from glass to air again, can you see here, the ray of light does not change direction. Well, the reason why it doesn't change direction here is because it's going along the normal. Now, what you do then is you record the angle of instance and the angle of refraction. Well, what you do is you then do measurements recording sine of the angle of instance and sine of the angle of refraction. Now, to show you this in a simulation happening, going here, is you can do it by switching a laser beam on here. Now here, light is traveling from air into glass, and you see it's bending towards normal. Now note, you've actually got a little bit of reflection here, and this has been one of the major problems that basically caused loads of problems for physicists many times, is the fact that it has a little bit of reflection and you've got refraction happening at the same time. And that's where quantum theory comes in, but that's another story. Now, what I'm going to do is I'm going to change my medium here to glass. And what you can do is you can basically put your protractor here like so. And I'm going to get it on. And what you can do here is I'm going to change the angle. And you can see here the angle is going to be 30 degrees. And that's the angle of instance. Now you can see here, so what I can do then is go back to my simulation. If I have my angle of instance, is then I would work out then sine 30 degrees. Now going back to the simulation, which is over here, I can then see here I've got 10, 20, 30, and the angle is about 19, 20 degrees. So then I thought I'd go back here, back to my result sheet, and that's going to be sine, I'm going to call it 19 degrees. Now, I'll leave you to do it. You then can work out sine 30 divided by sine 19 degrees. Now, you'll find that roughly equals 1.5. Okay? Then what you can do is you can do it the other way, where now I've got glass just here, and here's going to be the air, and here's going to be the air. Now the ray of light comes in. Again, when it hits the normal, it keeps going in a straight line. But I'm interested at this point here, where you have the angle of instance just there, and here's going to be your angle of refraction. This time though, I'm interested in going glass to air. Again, what you can do is work out the sine of the angle of incidence and the sine of the angle of refraction. Now going back to my simulation, which is over here. Now what I'm going to do is I'm going to flip these around. I'm going to have here is I'm going to have glass, and here is I'm going to have air. Now this time it's going to bend away from normal because I'm going from glass into air. Again, you get a little bit of reflection happening. Again, what you can do is you can measure angles here. You can see the angle of incidence is about 30 degrees, and this one now, what's that, 30, 40, going across here, there's 50, it's about 48 degrees. So again, what you can do is you can go back to your simulation here. What was I going to say? That was going to be about sine 30, and I think I roughly said about sine 48 degrees. And you find that approximately equals about 0.6. Now, then, compared to here, you'll find these two numbers is, if you do 1 over 1.5, it approximately equals 0.6. Therefore, they are the reciprocal of each one. Now, that is the link that actually then what Snell started to see. He kept doing all of these, the sine in angle of incidence, the sine of refraction, and he found always it was roughly about 1.5 within experimental error. He then went the other way around, going from glass going to air. For glass, he found roughly about 0.6 each time. Hence, he came up with Snell's law. And what he realized was the sine I divided by the sine R was always roughly constant. He then called that N the refractive index. And then if he went from glass to air, as I mentioned before, is about 1.5. He then went from air to glass, it's 0.6. He roughly noticed the fact N was the reciprocal, 1 over N. And this is what is meant by Snell's law. Snell's law states that the sine I divided by sine I is going to be constant. Now, it does depend on the medium. What I mean by that is, if I go back to my simulation here, I'm now going to put this one is going to be air, and this one is now going to be water. We get a different angle now. Now here, you've already got in the simulation, it shows you 1.3. In other words, the index of refraction, or the refractive index for air going to water is 1.33. It's different. And it starts making sense because the light is actually slows down by different amounts. And we have refractive index for loads of transparent materials. So the last thing I need to do going through in this little lesson is you need to be able to calculate the refractive index. So for example here, going to question A, here you've got the refractive index N going from air to glass is going to be 1.5. Now you've got the angle of refraction at the point of incidence. If the angle of incidence is going to be 30 degrees, they want you to calculate the angle of refraction. So you state your formula first of all. Well, N is equal to sine I divided by sine R. I know N is going to be 1.5. In the first one, it tells me the angle of incidence is going to be sine 30 degrees. And your sine R pops here. So what you do is rearrange the equation. You've then got your sine R is then going to be sine 30 degrees divided by 1.5. If you then take sine 30 is 0.5 divided by 1.5. Now when you do that in your calculator, you get 0.3, and then what you need to do is sine to the minus 1 of 0.3, and you pop out, I think it is about 19.5 degrees. And again, examiners want to see formula, working, answer, and units. We'll use comes straight 4 degrees here. Now, you can do these yourself. I think I've worked them out. Is that one pops down to 35.2 degrees. This one is going to be 59.4 degrees. And the last one is 74.6 degrees. Okay. What they do, these go around the other way around. So the last thing I want to show you is all to do with prisms, and these are interesting. But when you put light through a prism, and what I'm going to do, go through here in this one, is I can bring a prism just here like this, I can put my light on again. I'm then going to move it a little bit. Then I'm going to swing it down like this. I need to move it again. When light goes through a prism, we say you get something called deviation. And the reason why deviation means is simply the light ray goes here and suddenly it goes down here. Now, why you get deviation? Well, you get the light bending towards the normal again here and bending away from the normal just there. But you can see the sides are not parallel. And because the sides are not parallel, that is why you get deviation in a prism. But the interesting thing as well is you put different rays of light through. You look very carefully and move it back and forth. Again, can you see the angle or deviation it comes out is greater or smaller depending on red light to violet light. And this is why you can use prisms to actually split the light up and see the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. So what I've been through in this video is to recap, I've showed you, well, I described and explained the principle of refraction. You now know why it happens. I've stated Snell's law, and you've done some calculations. Hope you enjoyed the video.